Well, hey diddly-ho, neighborino. Welcome back to this video on parabolas. I have a little bit of an assignment for you. I want you to pick something that is not easily destructible off of your desk and just gently toss it across the room, okay? I want you to do that a couple of times, and as whatever thing you've picked is flying through the air, I want you to watch the path it takes. Go ahead. Here, I'll toss this thing. Okay. Do you have a guess for what that curve was? You saw it curved upward, hung in the air for an instant, and sort of fell back downward, going faster and faster as it fell. Well, it'd be weird if this wasn't the answer. It is a parabola. Any falling object, as long as wind resistance isn't extreme, so a feather wouldn't, but a hammer would, any falling object will describe a parabola through the air. So we can use parabolas as a model for thrown objects. For example, let's say you're standing at the top of a 100-meter tall cliff, and you want to get a feel for how far down it is. So you pick up a rock and you chuck it off the edge. You're going to yeet that rock at about 10 meters per second upward. That's like 18 or 20 miles an hour. So a pretty good throw, like a nice baseball throw. That's how fast it's going at first, but of course, the longer time goes on, it's going to slow down, and then it's going to start speeding up downward as gravity takes an effect on it. We want to know exactly how high the rock goes and exactly when it hits the ground, and we can use the tools from this section to answer those questions. Let's see. So first, we have to actually make a quadratic equation. In this class, this will be given to you. In a physics class, you'd have to make this yourself. But it turns out the equation here would look like this. So there's three terms. Did you know gravity affects everything on the planet negative 9.8 meters per second squared? Meters per second squared are the units for acceleration. It's how many meters per second you speed up downward every second. So let's round to 10. Let's say it was 10 meters per second squared. Then if I step off of the cliff, at first I'm motionless, and then in 1 second I'll be going 10 meters per second downward. After 2 seconds I'll be going 20, and then 30, and then 40, and then 50. So my speed is increasing by 10 every second I'm in the air, and then it's all stopping to zero very, very suddenly, and that's when the severe organ damage occurs. But until the severe organ damage occurs, your speed is increasing by 10 meters per second, well, 9.8 really, every second. 4.9 is half of 9.8, and I won't get into exactly why that is. Why should it be gravity times 1/2 of t squared? Well, it turns out that the instantaneous rate of change of 1/2 t squared is just t. So gravity times time is how fast you're falling. After 3 seconds, it's 10 times 3 is 30 meters per second. T is the rate of change of 1/2 t squared. So that's a calculus fact. We'll ignore that, but that's where the 1/2 actually comes from. So it's negative 4.9 t squared instead of 9.8. This is gravity. 10t is the initial speed. It was moving 10 meters per second upward. So as time goes on, it's moving 10 meters up the first second, and then 20 the second second. Well, that's what it would be doing if it weren't for gravity. The third term, 100 here, is how high it was to begin with. So I want to know, how high does it go? What is the top? How far up does this stone go maximum? And that's going to be right here. That's this height, right? Well, where did it reach that height? Right at the vertex. The vertex is the maximum or minimum of any polynomial, any parabola. Not any polynomial, just quadratic polynomials, just degree 2. But the vertex is the maximum or minimum. So here, since this opens downward, it's the maximum. If it opened upward, it would be the minimum, but that'd be a really weird path for a rock to take. So if I want to know how high it goes, first I find out where's the vertex, and that's going to be at t equals negative b over 2a. So negative 10 over 2 times negative 4.9 turns out to be 1.02. Now, unfortunately, that's a time. That's 1.02 seconds. That's when we reach the vertex. How high do we go? Well, that would be the y-coordinate. So how high we go is h of 1.02. So that's negative 4.9 times 1.02 squared plus 10 times 1.02 plus 100. And that turns out to be approximately 105. So the rock ends up 5 meters above where you threw it, and that's where it turns around and starts falling. So that's the answer to our first question. When does it hit the ground? Well, that's even easier. It hits the ground. So this is how high. When it hits the ground, well, that's when it has a height of 0, right? So that happens when h of t equals 0. Or in other words, when negative 4.9 t squared plus 10t plus 100 equals 0. Well, that's just a quadratic equation, and so we can use the quadratic formula. A is negative 4.9, B is 10, C is 100. So I write x equals negative b plus or minus root b squared minus 4ac 2a. In this case, that looks like negative 10 plus or minus the root of 10 squared minus 4ac. A is negative 4.9 here. So I'm going to cancel out the minus signs preemptively and just write plus 4 times 4.9 times 100. If you get those minus signs wrong, most of the time you get complex numbers. If you're getting the square root of a negative number, don't just try to force it to work. Understand it's almost certainly because you have the wrong sign on the term 4ac. 9 times out of 10, when I see someone who's stuck on the quadratic formula, it's because they have the wrong sign on this term right here. It's negative where it should be positive. So just check that you canceled the minus signs correctly. And then 2a is 2 times negative 4.9. Now we'll put that clickety-clack into our little calculators, and I get two numbers. If I do a plus, I get 5.65, and if I do a minus, I get negative 3.6. And these are times in seconds. So does the rock hit the ground after 5.65 seconds or after negative 3.61 seconds? Well, pretty clearly it's the one that's an actual amount of time we can have. The rock doesn't go back in time when you throw it, so it hits the ground after 5.65 seconds. Why are there two answers when only one is realistic? Well, on the diagram here, this is the point 5.65 comma 0. The vertex, incidentally, was the point 1.02 comma 105. The other root is negative 3.61 comma 0, and that's where the parabola would go if we drew the rest of it. So that's why you got that extra solution, but it's part of the parabola, it's not part of the actual diagram of the problem, so that's what we discard. So there you go. Pretty much any time I ask you to find a maximum or a minimum, it's going to be a vertex. So if I say, if our bakery make n cake, so we make some number of cakes, we'll call that number n. Let's say our profit is we'll have some diseconomies of scale. Let's say negative 3n squared plus 600n minus 80. So sure, why not? Let's say that this is in cents. How about that? Doesn't make sense if this is dollars. So costs us 80 cents to open for the day. We make $6 every time we sell a cake. But then the more cakes you flood the market with, the less you're going to be able to sell them for. So if you have a whole bunch of cakes, this negative quadratic term brings the price down over time. So our profit curve is going to look something like this. So my question is, how many cakes should we make to make the most money? If we make too many, no one's going to want to buy them. If we don't make enough, then we're not going to make the money from selling them. So if we're just concerned with maximizing profit, we can find out the maximum profit is this amount right here, and it's at this number of cakes. Well, that's the vertex. So I should make n equals negative b over 2a. So that's negative 600 over 2 times negative 3. I should make 100 cakes. If I make 101, my profit will go down by a little bit. If I make 99, my profit will go down by a little bit. 100 is perfect because we sell as many as people want. This is all assuming, this all assumes that the economics model you learned in school works. So if you're doing price discrimination somehow, then you can make more profit. But this is the basic model. This is Econ 101. If you want to do Econ 301, the model's more complicated. Okay, we should make 100 cakes, and the amount of profit we'll get is we plug that back into the function. We'll make negative 3 times 100 squared plus 600 times 100 minus 80. Well, let's see. This is negative 30,000. This is 60,000 and minus 80. So altogether, that's no, not a 3. 2, 9, 9, 20. Okay. We'll make $299.20 if we sell exactly 100 cakes, no more, no less. That's our profit. And just for fun, if you want, you could plug in. I can actually tell you exactly how much. I know if I go to the left or to the right, I'm going to drop. If I go 1 unit to the left or right, I'll drop by 3 because I know how parabolas work, right? So if I made 99 cakes, I would only make $299.17. If I made 101 cakes, I would make $299.17. You can plug it in and check for yourself that those are the numbers you'd get. So the vertex of a parabola helps you maximize profit in a simple economic model. Now, should you be maximizing profit or actually serving the community with the cakes? Well, that's up to you to decide. I say serve the community, but there's no equation for that. That's all about use your heart and not your brain for that. So here the parabola was a little bit abstract. It was our profits versus how many cakes we made. The next parabola is going to be even more abstract because this one's weird. It's a geometry problem, but the parabola isn't physical. So here's the dealio. You've got a building. No, let's say you've got a road. You've got a road running next to your business. And let me put the double yellow lines in the middle of the road. There we go. There's our highway. It's a straight line, straight highway. And your boss says, hey, I noticed we have 340 feet of chain link fence in the shed. It's burning a hole in my pocket. So boss says, hey, here's how much fence we got. I want you to take all that fence. You're going to spend your afternoon, hump out to the road with all that fence, and I want you to make me a rectangular parking lot. Something like this. And you say, well, boss, that doesn't give me a lot of information. Do you want the parking lot to be long and skinny or tall and narrow, perfect square? And the boss says, you're a smart kid. You took college algebra. Make it as big as you can. So this parking lot needs to be as big as possible, and it's up to you to decide how. You've got 340 feet of fence to use. Believe it or not, that's all the information you need to solve the problem. There is an actual solution. And the solution involves the vertex of a parabola. So here's what we do. If this is going to be a rectangle, then it's got to have a length and a width. So we've got the length here and the width here and here. We don't have to put fence along the road. The road is a natural boundary. So we've got length and 2 widths. And together, those have to be 340 feet. So I can write one equation. So now I've identified my unknowns, right? This is that problem-solving method from 3.1. My unknowns are going to be the length and width. And I know 2 things. I know that area is length times width. And I know that the 340 feet of fence, if I want it as big as possible, I'm guessing I'm going to have to use all the fence. So I'll make that go into my 2 widths and my 1 length. So now, the area, I just know I want it to be as big as possible. So what do I do with that? We'll worry about that in a second. In the meantime, I know from section 3.1 that having fewer unknowns is a good thing. So I'm going to try to reduce this down to 2 letters instead of 3. I'm going to try to, the L and the W are redundant somehow, and I want to work out how. I'm going to solve this bottom equation for L real quick. I'm going to write 340 minus 2W equals L, right? Just subtract 2W from each side. Because now what I can do is take this L and paste it here. Go on. Oh my God, it's so slow. Take this L and paste it here. I drew the blue lines right as I was saying it, and then that's how long it takes for it to show up on my screen. It's teaching online is wonderful. And what I get is A equals, the first L is 340 minus 2W, and the W just stays the same. And now I have A, well, it's more or less written as a function of W. In fact, I could make that explicit and say, this is A as a function of W, and what kind of function is it? Let me distribute and I'll tell you. 340W minus 2W squared. Would you look at that? It's quadratic. It's quadratic. Don't be fooled. This is B, the 340. A is negative 2. So if A is negative 2, it's stretched a little and it opens downward. The width can increase. Area is going to go up to a maximum and then fall back down. And that's because this parabola opens downward. Where's that maximum? At the vertex. So my vertex is going to be negative B over 2A. Now remember, B is the linear term. B is the term with no exponent. So that's the 340. A is the quadratic term, coefficient. So that's the negative 2. Negative 340 over negative 2 is positive. Something is wrong here. Oh my God. Oh my God. 2A, 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 2 times negative 2. 340 over negative 4 is 85, and that's the right answer. My spider sense was tingling, because if the width had been 170, scroll to the diagram, please. If the width had been 170, I would have gone 170 down and then 170 back and had nothing for the length. So I knew that wasn't right. Now 85 is a lot more reasonable. So the width is going to be 85. That's where the vertex is. If I make the width any bigger or smaller, the area shrinks. I can even find out what the area would be. I can say if the width is 85, well, first off, that means out of 340, that's the perimeter. I used 85 here and 85 here. 85 plus 85 is 170. 340 minus 170, so this is 340 minus 2 times 85 is what we've got left. That's 170 feet. So our rectangle is going to be 85 by 170. And 85 times 170 is 14,450. So we can make our boss a parking lot that is 14,450 square feet. The other way I could have got this number is if I plugged 85 in here, 340 times 85 minus 2 times 85 squared is also 14,450. So that's the biggest parking lot we can get. And if your boss gives you a hard time and says, hey, student, why not 86 feet? You can say, well, I know that this is stretched by 2 and it's upside down, right? So if I go 1 to the left or right, I go 2 down. You can say, boss, if I made it 86 feet wide, you'd only have 14,448 square feet of parking space. And before you ask, what if I made it 84 feet wide? Same thing, 14,448. It's 2 square feet if we go up or down by a foot of width. This is the optimum. Pretty cool, huh? So there you go. There's 3 good applications of quadratics and their vertices. And now that that's done, I'd say that's all for 5.1. I'll see you again for 5.2. We're going to be learning about polynomials. Polynomials are next. See you then.